Hello everyone. This week the focus is on continuous random variables. What are them? Well, many quantities in the real world are smoothly varying. So the height of a tree or the weight of an apple, it's not a discrete value like 1 gram, 2 gram, 3 grams, but it's like it could be 1.543 grams. So continuous random variables have a continuous sample space. So think like real numbers or positive real numbers, or certain random variables are just construed between 0 and 1. So if we want to model such outcomes that are continuous outcomes, we need a new kind of object called a continuous random variable that can take on any value in this within the sample space. Now, the math machinery when working with continuous random variables is completely different. So we can just sum over the individual outcomes, that there is infinitely many outcomes in a continuous way. So there's a continuum of outcomes. So the way we describe these random variables is using a probability density function. So it tells you where there's more probability. We call it density. And when we compute probabilities, we use integration. So the probability of the event, the random variable x is between a and b, is computed by calculating the integral from a to b. Here is the picture. So this is the integral is the area of the blue region here. Okay. So previously computing probabilities required summations. Now computing integral is done using integrals. So sounds like a big complicated thing, and it is. I mean, if you've never seen calculus, this will be a big step up. Now, to make this transition easy, I have a little just-in-time calculus prerequisites section, 2.4.2, which should bring you up to speed. Now, calculus has a reputation for being complicated because people are forced to do things using pen and paper. You're supposed to memorize a bunch of tricks and do all kinds of calculations in an exam setting. You know, the teacher is breathing down your neck and you have 1 hour to compute an integral. You know, even the notation looks scary. In fact, if you understand what calculus is trying to do, is just computing areas. So the integral of the function g, we saw the function g, between the input 2 and 6, that area here is, we write it like this. The best part, and why you don't need to worry about calculus, is this function. So the SciPy integrate module has a function quad, short for quadrature. So quadrature is the old term people use to describe the area calculation. Okay, so you give it the function and the limits, where you start integrating, where you end integrating, and it spits out the area, just like that. Any region of interest, you say the starting and the ending point, and it computes integrals for you. So this means it's good if you know calculus, but if you understand how to use this function, then you don't have to worry about computing integrals by hand. Okay, the notebook 24 continuous random variables has all the same examples, which I hope you will play with, experiment with. Okay, but this is very short. If you've never seen calculus before, you don't know about integrals, then I recommend you check out the calculus tutorial. So right now it's available as a separate PDF, but in the future this will become Appendix F. And this is optional reading. if you want to review some math, I want you to focus on section 5. So in the book, we have a compact summary of calculus and what are integrals. In the PDF tutorial, you have a lot more details. If you can print this out and read it in detail, I guarantee you'll know more about calculus than the average student, okay? Okay, once you know calculus, the rest of section 2.4 is on easy mode. Essentially, we're doing search and replace. Everything you know about discrete random variables, if you replace the summations by integrals, we get the same concept. So there's the probability calculations. You can create computer models for random variables. The methods are almost identical, except there is a probability density function now instead of a probability mass function. And throughout the section, we're going to use two examples: the uniform distribution and the normal distribution, the standard normal. Okay, so we start off easy. We show how to compute an integral, how to compute a probability, and then do the same thing using the normal distribution. So do I have to compute this integral? No. Python will compute it for me. You know, this looks scary, this not so much. Okay, you already know about cumulative distribution functions. Continuous variables, it's the same concept. It's the total probability up to and including b. So it's an integral with the upper limit is changing. Here's the picture. Integrate over this region. The value of the area is represented here by the height of this line. Similarly for the normal distribution. The inverse of the cumulative distribution, remember, if you need to compute the quantiles, you call the PPF method. Expectations, same idea. Instead of a summation, we have an integral. The mean and the variance. In this section, we talk about some new things like the skewness and kurtosis. You read about them. And then there's a worked example. So the kombucha population, the kombucha bottles, we started with that in the chapter introduction, but now that you know about the normal distribution, we can go into details and show all the steps and calculations based on that probability model. All of this is just one example. Maybe it repeats some of the concepts you already know about, but hey, it doesn't hurt to repeat, no? Expectations. It's a little bit like the hard disk example. We want to show some real-world useful calculations. Okay, we conclude with some foreshadowing. For the normal distribution, if you go 2 steps, so this is the mean of the distribution, and this is 1 standard deviation, 2 standard deviations, and if you go 2 standard deviations to the right, that interval contains 95% of the distribution, of the mass, of the probability. So most outcomes, 95.4% of outcomes of the random variable k will fall somewhere in that blue region. So that's why we call it the bulk of the distribution. If you go 3 standard deviations away, then you get 99.7%. That's like pretty much all of it. So that's a little foreshadowing how to, the distribution goes all the way to infinity, but if you cut off at the 3 standard deviations to the left and to the right, you get most of it. So that's one way to describe a high probability interval. the complement, so instead of the most likely events, you have the most unlikely events. So focus on figure B and C. So these red regions totally are less than 5%. And these red regions, which you can barely see, are less than 0. They're about almost non-existent. So we call them extremely unlikely events. Yada, yada, yada. Exercises coming as separate file. So why is this foreshadowing? When we do hypothesis testing in chapter 3, this will be one of the ways we measure when we've observed something interesting in a data set. When the null hypothesis is very unlikely. So according to the null hypothesis, we see something very unlikely. So we conclude, oh, something else must be going on here. But yeah, for now, it's just we're in probability chapter, so you don't think about hypothesis testing. Sorry about that, but by the time you see these concepts in hypothesis testing, I want you to have an intuition that the tails contain the unlikely values. All right, play with the notebook, check out the tutorial. Good luck.